Fundamentals of thermal radiation. So far we had considered the conduction and convection modes of heat transfer, which are related to the nature of the materials involved and presence of fluid motion among other things. We now turn out our attention to the third mechanism of heat transfer, which is radiation, which is characteristically different from the other two. We start this chapter with the discussion of electromagnetic waves, electromagnetic spectrum, blackbody radiation and blackbody radiation function together with Stephen Boltzmann and Planck's law and Wien's displacement law. Radiation is emitted by every point on a plane surface in all directions in the hemisphere above the surface. The quantity that describes the magnitude of radiation emitted or incident in a specific direction in space is the radiation intensity. Various radiation fluxes such as emissive power, irradiation and radiosity are expressed in terms of intensity. This is followed by discussion of radioactive properties of materials such as emissivity, absorptivity, reflectivity and transmissivity and their dependence on the wavelength, direction and temperature. So introduction, take example, this is your vacuum chamber, this is hot object. The hot object in vacuum chamber loses heat by radiation. So there is no other mode of heat transfer here, neither convection, neither conduction, because it is a vacuum, there is no medium. So radiation differs from other heat transfer mechanisms in that it does not require presence of material medium to take place. In fact, energy transfer radiation is faster at the speed of light and it suffers no attenuation in vacuum. Also, radiation transfer occurs in solid as well liquid and gases. In most practical applications, all three modes of heat transfer occurs concurrently at varying degrees. But heat transfer through an vacuum space can occur only by radiation. For example, the energy coming from sun is all by radiation. Unlike conduction and convection, heat transfer radiation can occur between two bodies even when they are separated by a medium colder than both of them. You can see here at 5 degrees Celsius, person is 30, fire is 90. So radiation is transferred through the colder medium. The theoretical foundation of radiation was established in 1864 by physics James Clerk Maxwell, who postulated that acceleration, charges or charging electric currents give rise to electromagnetic radiation. These rapidly moving fields are called electromagnetic waves or electromagnetic radiation, and they represent the energy emitted by matter as a result of changes in electromagnetic configuration of atoms or molecules. Electromagnetic waves transfer energy just like waves, and our electromagnetic waves travel at a speed of light in a vacuum where c is equal to this, almost 3 into 10 to the power 8 meter per second. Electromagnetic waves are characterized by their frequency and wavelength. Lambda is wavelength, v is the frequency, c is the speed of the light. So this is the relation. The product of wavelength and frequency is equal to speed of light. The speed of propagation in medium is related to the speed of the light in a vacuum, which is c is equal to c naught by n, where n is the index of refraction of the medium. The refractive index is essentially unity for air and most gases, and about 1.5 glass and about 1.33 for water. The commonly used unit of wavelength is micrometer or micron, where micro is equal to 10 to the power minus 6 meter. The frequency of an electromagnetic wave can range from less than a million hertz to a septillion hertz or higher, depending on the source. It is proven useful to view electromagnetic wave radiation as the propagation of collection of discrete packets of energy called photons or quanta, as proposed by Max Planck in 1900 in conjunction with the quantum theory. In this, each photon of frequency is considered to have the energy of E, where E is the energy of the photon, which is your Planck's constant multiplied by frequency, or you can replace this frequency with speed of light and wavelength. Now energy is inversely proportional to wavelength. This is electromagnetic wave spectrum. You can see cosmic rays has the higher energy and the shorter wavelength, then your gamma rays, then X-rays, then ultraviolet. Visible region comes in this range. They had moderate energy, and the weakest are your radio waves, TV waves and electrical power waves. Their lambda is higher and their energy is the lowest. Therefore, shorter wavelength radiation possess larger photon energies. It is no wonder that we try to avoid very short wavelength radiations such as gamma and X-rays, since they are highly destructive. Also, in case of X-rays, exposure to the X-rays is limited for fraction of seconds to avoid damage to the bones. Thermal radiation. Although all electronic waves have the same general feature, waves of different wavelength different significantly in their behavior. The electromagnetic radiation encountered in practice covers a wide range of wavelengths, varying from less than 10 to the power minus 10 micrometer for cosmic rays to the more than 10 to the power 10 micrometer for electrical power waves. So this is your cosmic and this is your electrical power waves. The electromagnetic spectrum also includes gamma and X-rays. Different types of electromagnetic radiation are produced through various mechanisms. For example, gamma rays are produced by nuclear reaction, X-rays are produced by bombardment of metals and high energy electrons. Microwaves are produced by some materials like magnetrons, and radio waves are by the excitation of some crystal or the flow of alternating current through the electric conductors. So this region, which is a shorter wavelength, which is gamma rays or with shorter wavelength, this is concerned with the nuclear engineers, while the long wavelength microwave and radio waves, these are concerned with the electrical engineers. The region which we concerned with the heat transfer, that is your thermal radiation in this region. So thermal radiation is constantly emitted by all matters whose temperature is above absolute zero. Means if you are sitting in a room, so you will emit radiation, plants, walls, furniture. The radiation will come around from every object which is having temperature above zero. That is everything around us, such as wall, furniture, our friends constantly emit radiation. Thermal radiation is also defined as a portion of electromagnetic radiation that extends from 0.1 to 100 micrometer. Means this 0.1 from here to here, 10 to the power 2. This is your thermal radiation. It also includes the visible region also. What we call light is simply the visible portion of the electromagnetic spectrum that lies between 0.40 and 0.76 micrometer. So light is characteristically no different than the electromagnetic radiation, except that it happens to trigger the sensation of seeing in human eye. So light or visible spectrum consists of narrow bands of color like violet in this band, then blue, green, yellow, orange and red. As the wavelength increase, their energy will decrease. A body that emits some radiation in the visible range is called light source. Sun is obviously our primary light source. The electromagnetic radiation emitted by sun is known as solar radiation, and nearly all of it falls in the wavelength 0.3 to 3 micrometer. The radiation emitted by bodies at room temperature falls in the infrared region of spectrum, which extends from 0.76 to 100 micrometer. Bodies start emitting noticeable visible radiation at temperature of 800 Kelvin. The tungsten filament of light bulb must be heated to temperature of 2000 Kelvin before it can emit any significant amount of radiation in the visible range. Ultraviolet radiations include low wavelength of the thermal radiation spectrum and lies between the wavelength 0.01 and 0.40 micrometer. So this is your ultraviolet region. It has more energy as compared to the visible radiations. Fortunately, the ozone layer in the atmosphere acts as a protective blanket and absorb most of ultraviolet radiation. Ultraviolet radiation is also produced artificially in fluorescent lamps for use in medicine as a bacteria killer and in tanning parlors as the artificial tanner. In heat transfer study, we are interested in the energy emitted by bodies because of the temperature only. Therefore, we will limit our consideration to thermal radiation, which we will simply call radiation. The radiations developed below are restricted to thermal radiation only and may not be applicable to other forms of electromagnetic radiation. The electrons, atoms and molecules, all solids, liquid and gases above absolute zero, are constantly in motion and does radiate some sort of radiation. So radiation is a volumetric formula. However, for opaque solids such as metals, wood and rocks, which you can see here, these are opaque, it is only surface phenomena, means radiation is emitted by the surface and can never reach the surface, means even if they absorb radiation, it will be absorbed within the few thickness of this surface. Note that the radiation characteristics of surface can be changed completely by applying thin layer of coating on them. Black body radiation. A body at a temperature above absolute zero emits radiation in all directions over a wide range of wavelength. The amount of radiation energy emitted from a surface at a given wavelength depends on the material of the body and the condition of its surface as well as surface temperature. Therefore, different bodies may emit different amounts of radiation per unit surface area even when they are at same temperature. Thus, it is natural to be curious about the maximum amount of radiation that can be emitted by a surface at a given temperature. Satisfying this curiosity requires the definition of an idealized body called a black body to serve as a standard against which the radiative properties of real surfaces may be compared. A black body is defined as a perfect emitter and absorber of radiation at a specified temperature and wavelength. No surface can emit more energy than the black body. The radiation emitted by black body per unit time per unit surface area was determined by Josh Stephen. It is EB, where it is called black body emissive power, which is Stephen Boltzmann constant to T raised to power 4. So it is a function of temperature in Kelvin and its fourth power. Another type of body that closely resembles a black body is large cavity with a small opening, as shown in this figure, with constant surface temperature. Radiation coming in through the opening of area A will undergo multiple reflections in the wall, and thus it will have several chances to absorb by interior surface of the cavity before part of it can possibly escape. Also, if the surface of the cavity is isothermal at temperature T, the radiation emitted by the interior surface will stream through the opening area after undergoing multiple reflections, and thus it will have a diffuse nature. Therefore, the cavity will act as a perfect absorber and perfect emitter. So the above relation, Stephen Boltzmann law, gives the total black body emissive power EB, which is the sum of radiation emitted over all wavelengths. But sometimes we need to know spectral black body emissive power for a corresponding to particular radiation range, which is the amount of radiation energy emitted by black body at an absolute temperature T per unit time per unit surface area and per unit wavelength about the wavelength lambda. For example, we are more interested in the amount of radiation an incandescent lamp bulb emits in the visible wavelength spectrum than we are in total amount emitted. So the relation for spectral black body emissive power was developed by Max Planck. So this is where C1 is equal to this, C2 is equal to this, T is the absolute temperature of surface, and lambda is the wavelength of radiation emitted, and K is equal to this, which is Boltzmann's constant. The relation is valid for surface in vacuum or gas. For other mediums, it needs to be modified by replacing C1 by C1 by n square, where n is the index of refraction of the medium. The variation of spectral black body emissive power with wavelength is plotted here below. So this is the variation of black body emissive power with the wavelength for several temperature. This is equal to 100 Kelvin. This curve corresponds to 300 Kelvin, and this curve corresponds to 500 Kelvin. This curve corresponds to 1000 Kelvin. As you increase the temperature, the energy emitted and your wavelength will shift to the left hand side. Means higher energy waves are emitted with lower wavelength. The emitted radiation is a continuous function of wavelength. At any specified temperature, it increases with wavelength, reaches a peak, and then decreases with increasing wavelength. At any wavelength, the amount of emitted radiation increases with increasing temperature. As temperature increases, the curve shifts to the left or to the shorter wavelength region. Consequently, a larger fraction of radiation is emitted at shorter wavelength at higher temperature. Means, so if you compare this 2000 Kelvin temperature with the lower temperature 100, you can see the maximum portion of radiation emitted lies in the lower wavelength as compared to this. In this case, the maximum energy is emitted in the form of radiation corresponding to the larger wavelength. So radiation emitted by sun is shown by this curve here at 5800 Kelvin. The radiation emitted by sun, which is considered to be black body at 5780 Kelvin, reached its peak in the visible region. So this is the visible region you can see here of the spectrum. Therefore, sun is in tune with our eyes, because our eyes are able to see the visible spectrum. On the other hand, surface less than 800 Kelvin emit almost entirely in infrared region. So this is surface which are less than 800 Kelvin. They will lie in this range. This is infrared region. The wavelength at which the peak occurs for a specific temperature is given by Weiss displacement law, which is equal to lambda T maximum is equal to 2897.8 micrometer Kelvin. So the relation was developed by Willy using classical thermodynamics, but it can also be obtained by differential equation with respect to lambda. So you should differentiate to this equation with respect to lambda, keeping temperature constant, and equate this equal to 0. You will get the same relation, because at the maxima your slope of this curve is 0. So if you join all the maxima on all the curve, this will form a straight line, and this is local of maximum power, which is Lt is equal to this. The peak of solar radiation, for example, occur at this 0.50 micrometer. You can see this is your solar radiation, and peak occurs at 0.50 micrometer, and the peak of radiation emitted by surface at room temperature 298 occurs at 9.7 micrometer. You can see the peak here, it is correspond to 9.5 micrometer wavelength, corresponding to 300 degree Kelvin temperature. Electric resistance heater starts radiating heat soon after it is plugged in, and we can feel the emitted radiation energy by holding the hand facing the heater, but the radiation is entirely in the infrared region and thus cannot be sensed by our eyes. The heater would appear dull red when its temperature is about 1000 Kelvin, since it will start emitting a detectable amount of visible red radiation at the temperature. As the temperature rises even more, the heater appears bright red and is said to be red hot. When the temperature reaches about 1500 Kelvin, the heater emits enough radiation in the entire visible range of spectrum to appear almost white to the eye, and it is called white hot. So 15 degree Kelvin, 100 Kelvin lies in this range. So if you say our visible spectra lies between 1 to 0.1 micrometer, so this is your visible spectra. So at this Kelvin 1500, the heater is visible, which is red hot. So there are few animals who can detect thermal radiations, but human eye cannot. So body heat coming of warm-blooded animals, and thus they can be see at night without using any instrument. Rattlesnake can detect infrared radiation. Similarly, honeybees are sensitive to ultraviolet radiation. A surface that reflects all the light colors, all the light appears white, while a surface that absorbs all light incident on it appears black. Suppose there is a surface, red, yellow, green and blue, these are the color of the light, they are strike with the surface, and all colors are absorbed, only red is reflected. So this color will, this surface will appear red. It should clear from the discussion that the color of an object is not due to emission, which is primarily in the infrared region, unless the surface temperature of the object is about 1000 Kelvin. Instead, the color of a surface depends on the absorption and reflection characteristics of the surface and is due to the selective absorption and reflection of the incident visible radiation coming from a light source such as sun or incandescent light bulb. A piece of clothing containing a pigment that reflects red while absorbing the remaining parts of the incident light appears red to the eye. Leaves appear green because their cells contain pigment chlorophyll, which strongly reflects green while absorbing other colors. The Stephen-Boltzmann law, which is EB, gives the total radiation emitted by black body at all wavelengths from lambda is equal to 0 to lambda is equal to infinity. But we are often interested in the amount of radiation emitted over some wavelength band. For example, an incandescent light bulb is judged on the basis of a radiation it emits in visible range rather than the radiation it emits at all wavelengths. The radiation energy emitted by the black body per unit area over a wavelength from lambda is equal to 0 to lambda is determined from the equation. So this is from 0 to lambda at particular temperature by integrating 0 to lambda for this equation. So we can find the emissive power for a particular wavelength from 0 to lambda by integrating this equation. But it turns out that the integration does not have a simple closed form solution, and performing a numerical integration each time we need to a value of EB 0, lambda, which is not practical. Therefore, we define a dimensionless quantity f lambda called Blackboard radiation function such that f lambda is dimensionless. It is the ratio of this integral to the black body radiation, which is sigma t raised to power 4. So this is dimensionless quantity. This is dimensionless quantity here, same, and this is lambda 1 and lambda 2 for particular wavelength. So you can find by integrating the function f lambda represents fraction of radiation emitted from a black body at temperature T in the wavelength band from lambda is equal to 0 to lambda. The values of f lambda are listed in table as a function of lambda t. So these values are listed here, lambda t and f lambda in this table. So the fraction of total radiation energy emitted by black body at temperature T over a finite wavelength from lambda is equal to 1 to lambda is equal to 2 here is determined from this equation. Now you can see here F lambda minus lambda 2 over temperature in this is equal to this area here. So this area here represent the fraction of radiation energy emitted from a black body at temperature T in the wavelength band from lambda 1 to lambda 2. Radiation intensity. Radiation is emitted by all parts of a plane surface in all directions into the hemisphere above the surface, and the directional distribution of emitted radiation is usually not uniform. Therefore, we need to quantify that describe the magnitude of radiation emitted in a specified direction in space. This quantity is radiation intensity denoted by I. Before we can describe a directional quantity, we need to specify direction in space. So take this is your emitted radiation. Theta is your angle with the z-axis of and with the radiation. This angle is called zenith angle. Now if you take the projection of this emitted radiation on xy plane, so you will get this dotted line, and the angle of this with the axis called phi, which is azimuth angle. Radiation intensity is used to describe how the emitted radiation varies with zenith and azimuth angle. In all surface emitted radiation uniformly in all directions, the emissive power would be sufficient to quantify radiation, and we would not need to deal with the intensity. The radiation emitted by a black body per unit normal area is the same in all directions, and thus there is no directional dependence, but this is not the case for real surface. Before we define intensity, we need to quantify the size of an opening in space. Solid angle. Let us try to quantify the size of slice of pizza. This is pizza, you have the slice. One way doing is to specify the arc length of the outer edge of the slice and to form the slice by connecting the mid end points of the arc to the center. Means these end points of arc, this point, if you connect here, you will get this slice here. The second more better way is just to define this angle alpha. At the center of this pizza, you can divide this angle alpha. So say angle of pi by 2 radian or 90 degree. For example, always represent a quarter pizza, no matter what is the radius. Whether your pizza size has radius 1 or 2, if the angle is 90 degree, it will represent quarter size of the pizza. For a circle of unit radius, the length of the arc is equivalent in magnitude to the plane angle it subtends. Both are 2 pi for a complete circle of radius r. Means this angle by arc at the center it is equal to 2 pi. In nutshell, we can say this angle represents this arc length. But this is in case of 2-dimensional. In 3-dimensional, we have to consider this case. This is a case of sphere. Here we have to follow a different approach. Now consider a water lemur and let us attempt to quantify the size of a slice. This is your slice. Again, we can do it by specifying the outer surface area of the slice, or by working with the angles for generality. We can take the angle of the slice at the center. We can measure that angle also, or we can take the surface area. So there are two methods. Now connect all the 4 edges of this slice to the center. You can see this is a cone here whose tip is at the center, and thus the angle at the center in this case is properly called solid angle. So this is called solid angle, which is omega here. The solid angle is denoted by omega and its unit is steradian. This in analogy to the plane angle, which is this alpha, or which is here this angle, we can say that the area of a surface of a sphere of unit radius is equivalent in magnitude to the solid angle it subtends. So in this case it is 4 pi for a sphere of radius r is equal to 1. Means this solid angle at the center by the surface is equal to 4 pi for a radius of r is equal to 1. So also we can show this differential by taking differential surface area on sphere ds, which is equal to r square sin theta d theta d phi. So this is ds surface area. So this angle is d theta at the center, and you can see this angle is your d phi here. So there are two angles here. One is this angle d theta on this surface. Another is on this surface on this side, which is this length. So this angle is your d phi. You can see the projection of this triangle on this side. This angle is d phi. If this angle is d phi, the radius of this sphere is suppose r. So this length is r d phi. Now we know this length is equal to r d theta because r is the radius and d theta is the angle by this curve at the center. So this is r d theta. Now we have to find this side. If you know this side, you can find this small element area by multiplying this side with this side. So this is, we know, theta, that is angle made at this vertical axis. So this is r. So this side is r sin theta. And we know this angle is d phi. This angle is d phi and this angle is also d phi. Now if you have to find this length, it will become d phi into this r sin theta. So it will become r sin theta d phi. Now when you multiply these two, you will get the surface area, which is ds, which is this r sin theta d phi r d theta. If you divide this by r square, you will get solid angle d omega, which in this case is sin theta d theta d phi. Now if you integrate this small element ds surface for the sphere, you will get total surface r square sin theta d phi. Integrate theta from 0 to pi and phi from 0 to 2 pi. After integration, you will get 4 pi a square, which is the area of sphere, which is formula for the area of sphere. For r is equal to 1, it reduces to s is equal to 4 pi. If put r here 1, you will get surface area is equal to 4 pi. And thus, the solid angle associated with a sphere is omega is equal to 4 pi into stereo. Means in case of sphere, this omega is equal to 4 pi. And for a hemisphere, it is 2 pi stereo. You can calculate also omega by integrating theta from 0 to pi by 2 and phi from 0 to 2 pi. You will get solid angle for a hemisphere, which is 2 pi here. You can also devise d omega is equal to ds by r square. Note that the area ds is normal to the direction of viewing, since ds is viewed from the center of sphere. Means this surface area is from the center of the sphere. In general, the differential solid angle d omega subtended by differential surface area dA when viewed from a point at a distance r from dA is expressed as d omega is equal to dan by r square. This is area normal to the this surface. This, you can say, if the light is coming from this direction, this area is a normal to that incident radiation. You can replace this dA normal with d cos alpha. Now suppose this is solid angle omega formed by this surface area A, and the radiation intensity is based on projected area. So you have to take the projection of this area, which is this. It does the calculation of radiation emission from a surface involve the projection of the surface. Now if you take the normal of this surface, which is this, and the angle between normal of the surface and this line is called theta. So in this case, projected area is equal to our this, which is a n is equal to a this area into cos theta. So same thing is explained here, where alpha is the angle between the normal of the surface and the direction of viewing, and thus dan is equal to dA cos alpha is normal area to the direction of viewing. Small surface viewed from relatively large distance can be approximately be treated as differential area in solid angle calculation. For example, the solid angle subtended by 5 cm square plane surface when viewed from a point O at a distance of 80 cm along the normal of the surface is, so omega is equal to an by r square, which is 7.81 in 10 per minus 4 stereo. If the surface is tilted so that the normal of the surface makes an angle of alpha 60 with the line connecting O to the center of surface, the projected area would be DAN is equal to dA cos alpha is equal to 5 cm square into cos 60, which is 2.5 cm square, and the solid angle in this case would be half of the value just determined, which is this. Intensity of emitter radiation. Consider the emission of radiation by differential area element dA of a surface as shown in figure. So this is your dA surface, and this area is responsive for emitters of radiation. We have to find when this radiation is maximum and at what angle this radiation is minimum. Suppose you are at this place, so this radiation will always flow perpendicular to the surface. It will in all directions, but the maximum radiation will at this point, which is perpendicular to this surface. You will receive maximum radiation, and when you just at this point, which is parallel to the surface, this surface which is emitting radiation, you will receive minimum radiation. So radiation is emitted in all direction into the hemisphere space, and the radiation streaming through the surface area ds is proportional to the solid angle d omega subtended by ds. So the radiation streaming, so this ds surface is proportional to this solid angle, which is our d omega in this case. It is also proportional to the radiating area ds as seen by an observer on ds, which varies from a maximum of dA when ds is at the top directly above dA when theta is 0. So if you watch from this side, you will able to see the whole area dA. If you say you are at this point, you will able to see whole area dA, means when your theta is 0, you will able to whole area. But if your theta will increase, you will move to this direction, you won't able to see the whole area dA. Now this dA will be minimum or 0 when your ds is at the bottom when theta is 90 degrees. Now take this ds at the bottom, and when ds is at the bottom, your theta will be 90 degree, and when you watch from here, the area dA will be minimum when ds is at the bottom. Therefore, the effective area of dA for emission in the direction of theta is projection of dA on a plane normal to theta, which is dA cos theta. So it means we can't consider this full area. We can't consider this full area. When you at this point, say you are in the direction of theta, you have to consider the projection of this area which is normal to this direction. Means you will take this area and you will project, will project in the direction which is normal to this ds surface. So the projection of dA on a normal to theta is dA cos theta. Radiation intensity in a given direction is based on unit area normal to the direction to provide a common basis for comparison for radiation emitted in different directions. The radiation intensity for emitted radiation I theta phi is defined as the rate at which radiation energy dq is emitted in the theta phi direction per unit area normal to the direction and per unit solid angle about this direction, that is I theta phi is equal to dq by dA cos theta d omega. So this is per unit basis. This is intensity in the theta and phi direction. If you put the value of d omega, you will get this relation here. The radiation flux for emitted radiation is the emissive power E, the rate at which radiation energy is emitted per unit area of the emitted surface, which can be expressed in differential form. So d is equal to dqv by dA. Put the value of dq from this equation into here, you will get this equation. Noting that the hemisphere of the surface will intercept all the radiation rays emitted by the surface. The emissive power for the surface into the hemisphere surrounding it can be determined by integration. The intensity of radiation emitted by a surface in general varies with direction, especially with the zenith angle theta. But many surfaces in practice can be approximated as being diffuse. For a diffusely emitting surface, the intensity of emitted radiation is independent of the direction, and thus I is equal to constant. You can remove this theta and phi, you can replace I is equal to constant. When you do so, you will get this equation. The equation will reduce, I will go out of this differential. So the emissive power relation in this equation reduced to the case of diffusively emitting surface, which is equal to pi I. Noting that the factor in equation is pi, this factor. You might have expected it to be 2 pi since intensity is the radiation energy per unit solid angle. So in this case solid angle is 2 pi because it is hemisphere, and the solid angle associated with the hemisphere is 2 pi. The reason for factor being pi is that the emissive power is based on actual surface area, whereas the intensity is based on projected area, and thus the factor cos theta that accompanies it as shown in figure this. You can see here, this is your projected area, which is A cos theta. So for black body, we know EB is equal to pi AB, where EB is equal to sigma T raised to power 4 is the black body emissive power. Therefore, the intensity of a radiation emitted by a black body at absolute temperature T is equal to EB by pi from this equation. Now replace this EB with respect to sigma T raised to power 4, which we know, well known relation, black body emission power. So you will get black body, in case of black body, intensity is equal to sigma T raised to power 4 by pi. Incident radiation, you can see radiation can receive by surface, by this surface. So all surface emit radiation, but also receive radiation emitted or reflected by other surface. The intensity of incident radiation, I incident theta phi, is defined as rate at which radiation energy dG is incident from the theta phi direction per unit area of receiving surface normal to the direction and per unit solid angle about this direction. Means we will take per unit solid angle and we will take per unit area normal to the direction. So here theta is the angle between the direction of incident radiation and normal of the surface. The radiation free flux on a surface from all directions is called irradiation. G, it is expressed as integral of dG from phi is equal to 0 to 2 pi, theta is equal to 0 to pi by 2. So I theta comma phi cos theta sin theta d theta d phi. Now say I is constant, when you integrate it will become, this irradiation will become G is equal to pi I. Again note that irradiation is based on the actual surface area and thus the factor cos theta, whereas the intensity of incident radiation is based on the projected area. Radiosity, surface that emit radiation as well as reflect it, and thus the radiation leaving a surface consists of emitted and reflected component. The calculation of radiation heat transfer between surface involve total radiation energy, which is sum of these two, with no regard for its origin. Thus we need to define a quantity that represents the rate at which radiation energy leaves a unit area of a surface in all directions. This quantity is called radiosity J, which is represented by IE plus R. Rest is the same as the previous case, and this is in case of hemisphere, where IE plus R is the sum of the emitted and reflected intensities for a surface that is both a diffuse emitter and a diffuse reflector. IE plus R is equal to constant, and the radiosity relation reduces to J is equal to pi IE plus R. Spectral quantities. So far we considered total radiation quantities and made no reference to wavelength dependence. This lumped approach is educated for many radiation problems encountered in practice, but sometimes it is necessary to consider the variation of radiation with wavelength as well as direction, and to express quantities at a certain wavelength lambda or per unit wavelength interval about lambda. Such quantities are referred to as spectral quantities. To draw attention to the wavelength independence, the modified spectral is used to indicate at a given wavelength. So spectral radiation intensity can be a function of lambda, theta and phi. For example, is simply the total radiation intensity per unit wavelength interval at lambda. The spectral intensity for emitted radiation can be defined as the rate at which radiation energy is emitted at the wavelength lambda in the theta phi direction per unit area normal to this direction per unit solid angle about this direction. So this can be expressed as this. The extra factor is your d lambda here. You can see the integration of a spectral quantity for all wavelengths give total quantity. So we are talking about this particular d lambda portion corresponding to which I intensity is equal to this. And if you integrate over the whole, you will get total intensity. Previously we had discussed about the total intensity. So the spectral emissive power then becomes, instead of this intensity, here now we'll use spectral intensity, which is a function of lambda, theta and phi. And same obtaination you can obtain for the irradiation, for the radiosity. The spectral intensity of radiation emitted by a black body at an absolute temperature T at a wavelength lambda has been determined by Max Planck and is expressed as I black body. Lambda is your spectral intensity. So lambda function of temperature, it is 2h c0 square by lambda raised to power phi exponential h c0 by lambda kt minus 1, where h is your Planck's constant and k is your Boltzmann constant and c0 is the speed of the light. So then the spectral blackbody emissive power can be expressed as a function of lambda and t, which is pi I b lambda into lambda t. Radiative properties. Most materials encountered in practice, such as metals, wood, bricks, are opaque to thermal radiation, and radiation is considered to be surface phenomena for such materials. That is, thermal radiation is emitted or absorbed within a few microns of surface, and thus we speak of radiation properties of surface for opaque materials. But some materials, such as glass and water, allow visible radiation to penetrate to considerable depth before any significant absorption takes place. Radiation through such semi-transparent material obviously cannot be considered to be a surface phenomena, since the entire volume of material interacts with radiation. On the other hand, both glass and water are practically opaque to infrared radiation. Therefore, material can exhibit different behavior at different wavelength. Means they are opaque to the infrared radiations, and thus dependence on wavelength is an important consideration in study of radiative properties such as emissivity, absorptivity, reflectivity and transmittivity of materials. Blackbody as a perfect emitter and absorber of radiation, and said that no body can emit more radiation than a blackbody at same temperature. Therefore, blackbody can be served as a reference in describing emission and absorption characteristics of real surface. Emissivity. The emissivity of surface represents the ratio of radiation emitted by a surface at a given temperature to the radiation emitted by a blackbody at the same temperature. Definitely, the normal space will emit less radiation as compared to the black body radiation. The emissivity of a surface is denoted by E and it varies between 0 and 1. Emissivity is a measure of how closely a surface approximates a body for emissivity which is equal to 1. The emissivity of real surface is not constant, rather it varies with temperature of the surface as well as wavelength and direction of the emitted radiation. Therefore, different emissivities can be defined for a surface depending on facts considered. The most elemental emissivity of surface at a given temperature is spectral direction emissivity, which is defined as ratio of intensity of radiation emitted by the surface at a specified wavelength in a specific direction to the intensity of radiation emitted by a black body. So you can say this is your emissivity, which is ratio of actual body, which is a function of wavelength at particular wavelength, and to the emissivity of, you can say, radiation emitted by the intensity of the black body, where subscript lambda and theta are used to designate spectral and directional quantities. For the black body, radiation intensity is independent of theta and phi, so you can replace it by IB. So then total directional emissivity, if you remove this lambda and integral over all wavelength, then you will get total directional emissivity for all wavelengths, which is defined like a manner by using total intensities as, which is theta phi t equal to IE theta phi t. Now here we will consider all the wavelengths, so lambda factor is removed here. So in practice it is usually more convenient to work with the radiation properties average over all directions called hemispherical properties. So surface area over the entire hemisphere is spectral emissive power. The spectral hemispherical emissivity can be expressed as in terms of this. This is for black body. Finally, the total hemispherical emissivity is defined in terms of radiation energy emitted over all wavelength in all direction. So if you move this lambda factor, you will get this T by EBT. You can take an example. Consider the emissivity function plotted in this figure here. You can see emissivity is varying from E1 to E2 and E3, where E1 is equal to constant, E2 is equal to constant, E3 is constant, but they will valid for a particular range of lambda. So then the average emissivity can be determined from the equation, which is equal to, from this equation you can calculate the average emissivity. So radiation is complex phenomena. So, and the consideration of wavelength and direction dependence properties, assuming sufficient data exist, makes it even more complicated. Therefore, we will consider average properties, and we will also consider the gray and diffuse approximations in the radiation calculations. A surface is said to diffuse if its properties are independent of direction, and gray if its properties are independent of wavelength. So in case of gray surface, diffuse surface, these three terms will be equal. Well, they are independent of wavelength and they are independent of angle, they are constant. This is for the diffuse phase. In case of gray surface, it is independent of wavelength. In case of real surface, neither they are independent on wavelength, neither they are independent on angle or direction. So it is very difficult to do the calculations for the real surface. So we will try to go for the calculation for gray surface or diffuse surface, or either both. Therefore, emissivity of gray surface, diffuse surface is simply the total hemispherical emissivity of that surface because of independence of direction and wavelength. A few comments about the validity of diffuse approximation are in order. Also, real surface do not emit radiation in perfectly diffuse manner as a black body does. They often come close. The variation of emissivity with direction for both electrical conductors and non-conductors is given in this figure. So this variation is the angle. Here theta is the angle measured from the normal of the surface, and thus theta is equal to 0 for radiation emitted in the direction normal to surface. Note that E theta remains nearly constant for about theta less than 40 for conductors such as metals, and theta less than 70 for non-conductors such as plastics. Therefore, the directional emissivity of a surface in normal direction is represented of hemispherical emissivity of the surface. In radiation analysis, it is common practice to assume the surface to be diffuse emitters with an emissivity equal to the value in the normal direction, theta is equal to 0. We also consider this gray surface approximation. So this is the black body emissivity, which is constant, fixed and maximum. This is real body emissivity, which will vary with the wavelength at constant temperature. And this is your gray surface emissivity, which is constant, independent of wavelength. Or you can say gray surface is emissivity and you can say emissive power of the black body. Product of this is your gray surface. This shows the typical range of emissivity for various materials. Polished metals have lowest emissivity, while plastic, paints, rocks and mineral, these are highest emissivity. Even oxidated metal have more emissivity compared to these. This is total normal emissivity with respect to temperature. You can see with increase in temperature, in this case emissivity will increase. For light oxide and stainless steel increase, heavy oxide, stainless steel increase, and in few cases it will decrease. This is also the variation of normal emissivity, spectral normal emissivity with the wavelength at this temperature. Absorptivity, reflectivity and transmissivity. Everything around us constantly emits radiation, and the emissivity represents the emission characteristics of those bodies. This means that every body, including our own, is constantly bombarded by radiation coming from all directions over a range of wavelengths. Recall that radiation flux incident on a surface is called irradiation and denoted by G. So this irradiation is denoted by G. This is total amount of radiation received by this body. Now when radiation strikes the surface, part of it is absorbed, which is your here alpha g, part of it is reflected, which is rho g, and part of it is transmitted through body, like water will transmit radiation, so it is tau g. Now this is transmittivity, this tau is called transmittivity, this is reflectivity, this is absorptivity, which is defined as the fraction of absorbed radiation to the total incident radiation, and reflected radiation, which is G reflected to the incident radiation, and transmitted radiation, which is G transmitted, this component, to the incident radiation, and these must lie between 1. Now as we know from the law of thermodynamics that sum of these three must be equal to the incident radiation. So when you put the value of here, when you divide this by G, you will get alpha density, or you can say absorptivity, reflectivity and transmittivity is equal to 1. Opaque surface, it means your transmittivity is 0. So when you will consider this only two factors, this means for opaque your absorptivity and reflectivity is equal to 1. So these definitions are for total hemispherical properties. Since G represents the radiation flux incident on the surface from all directions over the hemispherical surface overall wavelength, so thus alpha, or which can say absorptivity, reflectivity and transmittivity are average properties of a medium for all direction and all wavelength. The reflectivity differs somewhat from the other properties in that it's bidirectional nature. That is, the value of reflectivity of a surface depends only on the direction of the incident radiation, but also the direction of reflected radiation. You can see this is your incident radiation. So reflection can be in multi-direction. It can be in this form also, or your incident can be reflected by just as a single ray. So in this case, so first case is your actual or irregular, second is a diffuse case, and third is specular or mirror like. So therefore reflection rays of a radiation beam incident on a real surface in a specific direction will form an irregular shape. Such detailed reflectivity data do not exist for most surfaces, and even if they did, they would be of little value in radiation calculation. So in practice, for simplicity, surfaces are assumed to reflect in a perfectly specular or diffuse manner, means we will consider this case or this case. In specular reflection, the angle of reflection equals to the angle of incident of radiation beam. In diffuse reflection, radiation is reflected equally in all directions. Kirchhoff's law: consider a small body of surface area AS, emissivity E and absorptivity alpha at temperature T contained in large isothermal enclosure at same temperature as shown in figure. So this is small body contained in a large isothermal enclosure used in the development of Kirchhoff's law. AS is your surface area, E is your emissivity, alpha is absorptivity. It is emitting radiation and it is absorbing radiation. Recall that a large isothermal enclosure forms a black body cavity regardless of radiation properties of the enclosure surface, and the body's enclosure is too small to interface with the black body nature of the cavity. Therefore, the radiation incident on any part of surface of a small body is equal to the radiation emitted by a black body at temperature T. That is, G is equal to EBT is equal to sigma T raised to power 4. Means this is your radiation, and the radiation absorbed by small body per unit surface is equal to G absorbed is equal to absorptivity into irradiation, which is equal to this. Now radiation emitted by the small body is equal to this emissivity into sigma T raised to power 4, because this is enclosed container and the small body is in thermal equilibrium with the enclosure. Net heat transfer to the body must be 0. So there these two must be equal. It means emissivity is equal to absorptivity. That is, the total hemispherical emissivity of a surface at temperature T is equal to the total hemispherical absorptivity for radiation coming from a black body at the same temperature. This relation, which greatly simplifies the radiation analysis, was developed by Gauss of Kirchhoff and is now called Kirchhoff's law.